So welcome everyone. Welcome. My name is Michael Thiele. I'm the Manitoba Grazing Club coordinator, and this winter we've been doing a number of webinars. And tonight we have Darren Qualman with us. And I've got to know Darren over the last few years, and thought I'd just do a quick intro and then let Darren get going. So I grabbed a few words off of his website. I'd recommend check out his website, darrenqualman.com. He put down here, he's a long-term thinker, civilizational critic, researcher, data analyst, avid observer of the big picture. But I would say foremost, you got to put top of the list there. He's a Saskatchewan farm boy, so that gives him some street cred. He's south of Saskatoon. He recently published a wonderful book, and I totally recommend that you get a copy, read it, Civilization Critical. And you know what? Read it more than once. You're not gonna take it all in one reading. I've gone back to it a bunch of times, but maybe that just proves I'm a slow learner. Yeah, I know yeah, it's a great book. I guess the way I've kind of summarized it is it's a wonderful summation of the of our modern predicament. He's also a pretty well-educated guy. He's got a BSc in biology, BA in history, another BA in political science. He's back working. Darren's back working with the National Farmers Union. He worked back 1996, 2010. And then I think he probably took a few years there to write the book and do a few other things. And so now he's back with the NFU. He's the Director of Climate Crisis Policy and Action. Darren's talk this evening will focus in on the many climate and ecological problems caused by nitrogen fertilizer, what we can rightfully describe as a nitrogen crisis. But we're going to talk about the problem, but we're also going to talk about solutions and opportunities. So try to have a full discussion. And as part of that, we will have time for questions and discussion. And we have not a huge sized group, so I think we can do both here. If you want, you can type your question in the chat and I'll read it out in order. Or I think we can probably do simply, we'll go through, and if you want to unmute and ask a question, have a discussion with Darren, we can do it that way too. So with that, we'll get started. Welcome, Darren.
Thank you, Michael. That was a lovely introduction. And thanks to everybody for being here tonight. Thanks for the opportunity. Thanks for the interest. I really appreciate people taking part of their evening to listen to a bit of what I have to say, and we'll have lots of time, as Michael says, to hear from others, answer some questions, have a little bit of discussion. So I'll just share my screen here, get a PowerPoint presentation going. There we go. Is that up and working, Michael?
Yep, looks good.
Very good. So what I'm going to tell you tonight is I'm going to try and take a really big picture look at how the Earth system works and how agriculture works, how it's worked in the past, how it works now. And I'm going to do that to give you some new information and some new understanding of how materials like fossil fuels and nitrogen fertilizer and phosphorus move through the system and why they might be expected to cause some problems. At the heart of my talk is going to be a little bit of background about how in the past the main flows in the biosphere and in agricultural systems were circular, how the great innovation of the 20th and 21st century was to replace those circular flows with linear, and why those linear flows do two things. They make agriculture and other human systems incredibly powerful and productive, but they also cause a lot of problems because the stuff that goes into one end of those linear systems comes out the other. And I'm going to focus in on nitrogen. The nitrogen we push into one end of the system comes out the other. And I say all that so that you kind of understand where I'm going here, because I'm going to talk about 10,000 years of agriculture. I'm going to talk about how we changed it in the 20th century. I'm going to talk a little bit about carbon atoms and nitrogen atoms. And I just want you to be aware, kind of have a general idea of where this is going so that you don't just wonder, you know, what are we on about here? So I'm going to launch into my talk in a moment, but first I just want to show you where you can get a little bit more information if at the end of the evening or tomorrow, or you're reflecting on this and you're wanting a little more information. There's a couple sources I'd point to. On the screen right now is 3 2-page flyers that we put together. They're on the NFU website. So if you just go to nfu.ca, you'll see a big blue button that says climate change. Just click on that, it'll take you right to these 2-page flyers. Really quick little reads, give you a real good sense of both the problems around climate and agricultural emissions, but also the solutions. The solutions politically, but even the solutions that you can undertake on your own farm. Those are 2-pagers, kind of a quick read. If you want to do a deeper dive, I think Michael mentioned this report, came out a year ago. It's called Tackling the Farm Crisis and the Climate Crisis. It's 100 pages long, and it goes in detail, looks at farm income, it looks at nitrogen fertilizer, it looks at solutions, problems. It is the result of many people's work, and I think it's among the very few really deep dives into the question of climate change and agriculture and emissions reduction that focuses on the Canadian context and especially the Canadian prairies. So if what I say tonight raises your interest, raises questions, if you don't get everything you need tonight, you can check out this report, or you can give me an email and I'll put my email up at the end. So that's where you can get more information, that's background. So I'll just launch right into my talk. It's got 4 parts. The first part is about breaking loops. And I just put this picture up for a couple of reasons. One, it gives you a sense of where I'm zooming in from tonight. That is the farm where I grew up, where I farmed for many years, and where I still live. It's not quite that snowy here anymore. A lot of the snow is gone in the last week, but that's what it looked like earlier this winter. I put that picture up not just because that's a nice attractive barn and solar panels, but because I think that those 2 things, that barn and those solar panels, can really ground this talk a little bit because they're really, really symbolic. Now, that barn was one of the last big barns built on the prairies to house draft horses. It wasn't built for beef cows or dairy cows. It was built for horses. That was going to be the pulling power center for a really big agricultural operation. That barn was finished in 1918, and that was extremely poor timing for 2 reasons. One, the man who had it built, Mr. Rystrom, died in the Spanish flu epidemic of 1918. So every morning when I make my coffee, I look out the window, I see that barn, and I'm reminded what can happen during pandemics. But the other reason that the timing was bad when it came to that barn is 1918 is a very interesting year if you're a horse farmer. It's the absolute end of that era, and I'm going to show you a very cool graph of Canadian horse numbers and tractors here in a minute, and you'll see why 1918 was exactly the wrong year to invest massively in a horse barn. But it was the tail end of that horse-powered agriculture. And I just want you to think about what that means. Humans have practiced agriculture for about 10,000 years. And for 9,900 years, for 99% of the time that we've practiced agriculture, it has been solar powered, low input or no input, 0 net emission. You know, the kind of agriculture that took place around that barn is the tail end of thousands of years of agriculture that was powered by the sun, that was largely self-supplying and self-sufficient, that required no inputs, required no fossil fuels, that emitted very little or nothing into the atmosphere. So that barn really represents the end of thousands of years of solar powered, low input, low emission agriculture. And those solar panels represent a possible future, maybe, or at least the possibility of a future where we move back a little bit in that direction toward a lower input, lower fossil fuel, lower emission future. So I think that barn marks the end of one era, and maybe those solar panels hint at the beginning of another era. So I just want to get a little more explicit here with kind of my argument regarding circular versus linear flows, and how the agriculture of today is very different than the agriculture that held for 9,900 years until the early part of the 20th century. If you think about the biosphere, about nature, everything moves in a circle. We're all familiar with the water cycle. The sun raises water up through evaporation and goes to the clouds. It falls from the clouds back to the land, raised back up to the clouds. Water moves in a circle, the water cycle, hydrological cycle. The same thing with fertility. A lot of the major nutrients like nitrogen and phosphorus move in a circle. They might be in a plant for a while, and then the plant dies and decays, and they go back into the soil, and then another plant picks them up, that nitrogen atom, that phosphorus atom, as parts of different kinds of molecules. So most of the main building blocks of life, nitrogen, phosphorus, carbon, move around in a circle from the soil into a plant, maybe through the air, back into the soil, back into a plant. It's a circular flow, not linear. Even energy, and this gets back to that barn again. In traditional agricultural systems, there was a circular exchange of energy. The land provided the energy for the people and the draft animals, and the people and the draft animals expended some of that energy back on the land to grow more grain and food to power it again. So the source of energy for the farm was the farm. The farm fields gave food to the people, and gave grass and hay and grain to the animals, and they in turn used some of that energy to produce more of that food and grass and hay and grain. So there was a circular exchange of energy on the farm. There was a circular flow of seeds, of course. Crops would produce seeds, seeds would produce new crops. There's even a circular flow of things like knowledge. The farmers would observe what was happening in the landscape, and they would internalize that knowledge. And then the next year they would externalize that knowledge onto the landscape in the form of planting decisions, livestock selection, and then they would observe that and then internalize and externalize with a circular flow of knowledge from the landscape back to the farmer, and from the farmer back to the landscape. So what I'm saying here is agriculture was a system in which all the major energy and material and even knowledge flows were circular. There was no external flow coming into the farm and then going out the other side. It was just about everything that went into farming came out of farming. There weren't any farm input industries for about 9,900 years. And this is to be expected because agriculture came out of the biosphere, and that's the way the biosphere works. For millions and hundreds of millions of years, the ecosystems thrive because they manage to move things like phosphorus and nitrogen and carbon in tight, closed recycling loops. If they didn't do that, they would deplete, they would run out of those things, and these ecosystems would quickly wind down, and they'd lose their fertility. So the way the planet works in most cases is to move everything in a circle. Now, what I'm about to turn to is a description of how modern agriculture works, and that's very, very different. The great innovation, the great strength, and also the great weakness of modern agriculture is we took those circular flows of nitrogen and phosphorus and energy supplies and even seeds and knowledge. We took those circular flows, we cracked them open, we stretched them out, we made them linear, and we found ways of pushing more and more inputs into one end so that we could push more and more food out the other end, but also other things were coming out the other end too, like greenhouse gas emissions. And we're going to talk quite a bit about that tonight. So I'll just walk you through the loop breaking. And the loop breaking started right around 1918 when farmers went from horses to tractors, when they went from field work powered by the fields themselves to field work powered by distant oil fields. So this is a graph, Canadian data, covers the period 1910 to 1980, so about 70 years. The units aren't important, it's just the shape of the graph that is. So that blue line that goes up is the number of tractors in Canada, and the brown line that mostly goes down is the number of horses on farms. And you'll see marked in red, the red triangle and the red square, that is 1918. And you can see there's a real strong inflection upward in the number of tractors around 1918. That's why the man who built my barn had such bad timing. He got it finished just in time for tractors to rapidly displace horses in Canada and in the United States and a number of other countries. So, of course, there were tractors on farms before 1918. Most of them were big steam tractors, but they're really too big and heavy and expensive for the small quarter section, 2/4, 3/4 farms that we had in the prairies. Farmers couldn't afford them, couldn't really keep them working. So instead they were used in places for breaking sod or for spinning a threshing machine. But most farms didn't have a tractor. Most farms relied on horses right up till 1918 and to some extent beyond. But around 1918 and the final months of the First World War, several things came together. One, people were very interested in finding ways to farm that didn't require so many people. So replacing workers with tractors was a way to free up people to fight the war. Two, we had a lot of factory capacity, a lot of productive capacity because of the war. Factories were getting very good at producing internal combustion engines and metal machinery as part of the war effort. And probably most important, around 1918, a whole new type of tractor came on the market. Ford introduced the Fordson in 1917, the John Deere Model D shortly after that, and a little bit after that, the McCormick Farmall. So suddenly, instead of these great big coal-powered tractors, there were small, light, affordable, liquid fuel-powered tractors that were more suited to work on farms, and it was a very rapid takeoff starting in 1918. So the reason this is important is what we're seeing in this graph is a transition from a circular flow where farms supplied their own energy to a linear flow where petroleum was taken out of the ground, moved across the landscape to the farm, into the tractor, out the exhaust pipe, and into the atmosphere where that CO2 would stay for about 1,000 years. So that's the energy. The system was linearized with the use of fossil fuels. This is fertility. Until the mid-20th century, most of the fertility on farms for thousands of years was cycled within the farm, either natural fertility or from legumes or manures, various crop rotations, etc. I think a lot of you are very knowledgeable about how you can create fertility and manage it and cycle it without external nitrogen. But mid-century, that all changed, and you can see a fairly rapid increase in the tonnage of nitrogen fertilizer in Canada. Fertilizer tonnage has doubled since 1992, and we're going to talk quite a bit about nitrogen fertilizer here tonight. But what's clear here is after 9,950 years of circular flows of fertility, we installed what is now largely a linear flow system for fertility. It comes out of the potash mine or out of the phosphorus mine or out of the nitrogen fertilizer factory. It's trucked to the farm. It goes through the farm fields, and a lot of it comes out the other end, either in the food or as emissions into the atmosphere or waterways. It's a linear flow fertility system that had never existed on Earth, either in natural or agricultural systems before the middle of the 20th century. Seeds, same thing. Instead of seeds being something the farm produced for itself from its own crops, increasingly seeds became linear, coming from high-tech companies and labs at the one end, passing through the farm for 1 year, going out the other end in the crop, and being purchased anew each year. So you've got this linear flow of seeds replacing the circular flow. Same thing with knowledge. I said before that most of the knowledge for the farm used to come from the farm. The farmer would observe his or her own fields and then apply that knowledge next year. The source of the knowledge was the farm, and the destination of the knowledge was the farm. That's no longer true. We often don't stop to think about it, but there's this huge linear flow of knowledge into our farms and out the other end. Knowledge comes in the form of custom blended fertilizers, exotic chemistry, pesticides and insecticides, herbicides, very, very complex machinery with computers embedded that either we can't fix because it's too complicated, or we can't fix because the manufacturer won't give us the codes or the parts or the information to fix it. Incredible amounts of knowledge are purchased by farmers every year, pushed through the farm, obsolesced out the other end, and then new knowledge in the form of fertilizer and seeds and genetics and fertilizer blends, etc., are brought in year after year. So there's a linearization even of knowledge. Herbicide and insecticide, a lot of tonnage there. This is a graph that shows you Canadian insecticide and herbicide use from 1990 to 2010. Canadian insecticide use doubled in that 20-year period, and herbicide use nearly tripled. So everything that you can think of that's going into farming is going in at an increasing rate. We not only have linear systems, but we have linear systems that we're pushing more and more and more stuff in each and every year. So the thing I want to get across at this point is these are linear systems, and I want us to understand that, because that is going to help us understand why things like nitrogen get to be a real problem. So the part 2 of my talk is what goes in must come out. And the subtitle is, in which greenhouse gas emissions from agriculture are revealed as a product of farm inputs. So the linear flow structure of our civilization is causing a lot of different problems. Often we think of various so-called environmental problems as distinct, unique, not connected to each other. I would make the case that just about, not every, but almost every environmental problem you can think of isn't actually a unique problem. They all are a result of an underlying problem, and that underlying problem is linear flow systems. So all of these environmental problems that I've got on the screen here, climate change, ocean dead zones caused by too much phosphorus and nitrogen entering the ocean, algae clogged lakes, again, nitrogen and phosphorus, plastics in the ocean, toxicity in various places, resource depletion, etc. All of those are actually, even though they seem like separate and unique problems, they're all just symptoms of one underlying cause, and that is linear flow systems in which we push more stuff in one end and more stuff comes out the other. So I promise this is my only chemistry slide. Not everyone liked chemistry. I'll just, it says a 30-second review, it might only take 20. Atoms are indestructible. If you have a certain number of carbon atoms in either carbohydrates or hydrocarbons or carbon dioxide, you can do a lot of things to them. You can eat them, you can burn them, you can turn them into various things, including plastic. But at the end of the day, every carbon atom that went into the system is still there somewhere. If you have 100 carbon atoms at the beginning, you're going to have 100 carbon atoms at the end. They might just not be where they all started, you know. And we know this. Some carbon dioxide goes into a leaf of lettuce. The lettuce turns it into carbohydrates. We eat that lettuce. We metabolize it, and those carbohydrates are broken down, and out it comes as carbon dioxide. But the number of carbon atoms from the air into the lettuce, into us, and out through our breath that number of carbon atoms is preserved because they are indestructible. Same for nitrogen atoms, phosphorus atoms, all atoms. So what that means is all the atoms that we push into our linear agricultural systems come out the other end, every single atom. So carbon atoms go in the form of fossil fuels, and carbon atoms come out in the form of CO2, carbon dioxide. This causes a lot of problems, two of which are climate change and ocean acidification. This is a graph of 800,000 years of carbon dioxide concentrations in the atmosphere. Complicated graph, but I just want you to note two things. Over that 800,000 year period, CO2 concentrations went up and they went down, but note that never once did they peak above 300 parts per million. 300 parts per million was kind of the long-term record high before the modern period. But now we've got CO2 concentrations at about 420 parts per million, and they'll almost certainly peak above 500 because we're not very good at curtailing our emissions yet. So first thing is we've got CO2 concentrations in the atmosphere that are much, much higher than at any time in the last 800,000 years. The other thing, in addition to the fact that they're higher than what we see in kind of the long-term data, and I should just note, for those of you who are wondering, 800,000 years is a long time. It's 4 times longer than human beings have existed in our present form. So it's not a short period of time. So not only is CO2 high, it's rising very fast. And I'll just move my cursor around. Down here at the bottom, that's the sort of the peak of the last ice age, and then as CO2 goes up, some of the ice starts to melt. But what's important to note here is from the depths of the last ice age up until about 1900, there was a rise in atmospheric carbon dioxide of about 100 parts per million. And then it went up another 100 parts per million between 1900 and now. But this first rise of 100 parts per million took 10,000 years, but the most recent rise took just 100. So CO2 concentrations are rising about 100 times faster than what we see in the geological record. And scientists are very confident that you will not be able to find any period in history of the planet when CO2 concentrations went up that fast. To gain 100 parts per million in 100 years is really quite astonishing. As I say, about 100 times faster than what we would normally see. I'll just say one more thing about that graph. What you're seeing there, and this gets back to the linear flow systems, you know, lots of people talk about CO2 concentrations, but the way I think we can understand this that's new is this. What we've done since the beginning of the fossil fuel age, the last 200, 300 years, what we've done over that period is we've punched about 500 billion tons of carbon atoms. 500 billion tons of carbon atoms into the Earth system, into the economy, etc., in the form of coal and oil and natural gas. And every one of those atoms, the entire 500 billion tons of carbon atoms, has come out the other end, and they've now lodged themselves in our atmosphere and in our oceans. And these carbon dioxide stays in the atmosphere for hundreds of years. Most of it stays for about 1,000, so it's all still up there. So that 500 billion tons of carbon that we've pushed through our Earth systems and our economies in the form of fossil fuels, it's all there, and it is causing problems. So again, everything we push in comes out. Carbon atoms go in the form of fossil fuels and other sources, and carbon comes out as methane, CH4. Some of you will know that methane is the main component of natural gas. Methane is a very powerful greenhouse gas, about 28 times more powerful than carbon dioxide. The main sources of methane are oil and gas production. As I mentioned, natural gas is methane, and when we produce oil and coal, a lot of methane gets vented. A lot of methane leaks out of the natural gas distribution system. So the main sources of methane are fossil fuel production, also landfills, rice paddy agriculture, and grazing livestock. Methane comes out of the mouths of cattle when they digest grass because their stomachs are anaerobic, and bacteria cannot metabolize the energy in there to CO2, so they metabolize it to CH4. There's no O's in there, no oxygens, so they use hydrogen and they respire CH4. So we get climate change and a number of other problems. This is a graph of global methane concentrations in the atmosphere. A little shorter term than the last one. Instead of 800,000 years, it's just 10,000 years. You can see that for about 9,800 years, up till about 1800, methane concentrations in the atmosphere were about flat, and then they've spiked quite dramatically, and we're now at a point where they're about 3 times higher than they were naturally. Moving from carbon onto nitrogen, nitrogen atoms go in the form of fertilizer, and nitrogen atoms come out as nitrous oxide and other nitrogen components, and we get things like climate change, ocean dead zones, terrestrial ecosystem damage, etc. This is a graph, this is the front page of a report in the journal Nature, one of the 2 most prestigious and oft-cited journals out there. This is from Nature 2009. Stefan Rockström and anyway, last name's Stefan and Rockström. I can't remember the first names. And in this paper, they develop an idea of a safe operating space for humanity and the idea of planetary boundaries. You know, when humans intervene in the biosphere, at what point do we intervene too much and cause problems that start to threaten ourselves and other species in the planet? And I'll just zoom in on that graph from the report. So this circular graph is an attempt to kind of assess and quantify the extent of human interventions, and it looks at things like climate change, freshwater use, land use, ozone depletion, etc. And the green circles in the middle, they indicate a safe operating space. So where those red wedges are in the green, that means those are places where we haven't yet transgressed the planetary boundaries. We're not in the danger zone. But the wedges that extend past the green or far past the green, those are places where we have exited the safe operating space for planet Earth. We've pushed past the planetary boundaries, and we're causing a tremendous amount of damage and creating a lot of risk. And you can see there's 2 places where that's happened, and I think a lot of people could easily guess the first one, and that's biodiversity loss. A lot of you might know that we're in the fastest extinction event in 65 million years. Not since the asteroid hit the planet and extinguished the dinosaurs have we been shedding species as fast as we are now. So biodiversity loss doesn't surprise anyone, but I don't think 5 people in 100 could have named the other place where we have pushed farthest past the safe operating space, and that's that wedge on the right, and that's the nitrogen cycle. Humans have intervened massively in the planetary nitrogen flows. If you quantified, and scientists have done this, the amount of nitrogen that was moving through terrestrial ecosystems before the 20th century, and if you quantify it today, what you'll find is that the amount of nitrogen today moving through those terrestrial ecosystems, and terrestrial ecosystems is just a fancy way of saying the land, forests, wetlands, grasslands, farm fields, pastures, jungles, savannas, that sort of thing. The amount of nitrogen flowing through those terrestrial ecosystems is triple what it used to be before humans intervened. And those of you that use nitrogen know that it's a powerful plant nutrient. It really changes what happens on the landscape. So imagine if you triple the amount of nitrogen flowing through terrestrial landscapes on Earth. And because we don't use it spread equally over the Earth, we tend to concentrate our use in certain places. Lots of parts of the Earth, farming areas of North America, Europe, Asia, etc. The multiplication of nitrogen flows is tenfold, and in some cases, it's approaching 100 times natural levels, massive human interventions in nitrogen flows. I would say that if we didn't have the climate problems that we have, if we weren't talking about a climate crisis, we would be talking about a nitrogen crisis. And again, it's really easy to see why this is the case. We've got a linear flow system. We're pushing 100+ million tons of nitrogen atoms into one end, and that entire 100+ million tons of nitrogen is coming out the other end and finding its way into the air as a greenhouse gas, nitrous oxide, into the oceans, into the rivers and streams, etc. Global nitrogen use doubled since 1980. As I said, we're up over 100 million tons of actual N, so N atoms, 100 million tons every year, and still trending upward. Nitrogen is a greenhouse gas problem because nitrogen is an energy product. If you went to a nitrogen fertilizer factory, you'd see a big natural gas pipe going in one side and a big nitrogen gas pipe coming out the other side, nitrogen gas being anhydrous ammonia. And the hydrous is then made into granular fertilizers. It's so energy intensive that it takes the equivalent energy of about 2 tons of gasoline to make and apply 1 ton of nitrogen fertilizer. Of course, it's not made out of gasoline, it's made out of natural gas. And nitrogen fertilizer is unique amongst all the human materials and products and processes in that it's the only one that manages to be a major source of all 3 of the major greenhouse gases. So when we use nitrogen fertilizer in the soil, we get emissions of nitrous oxide, 300 times more powerful than CO2 as a greenhouse gas. When we manufacture it, carbon dioxide, and the main feedstock is natural gas, and the production and shipment and pipelines for natural gas are major sources of the 3rd major greenhouse gas, which is methane. This is the Koch brothers fertilizer plant in Brandon. That's a nitrogen fertilizer plant. You're looking at the biggest single source of greenhouse gases in all of Manitoba. So let's zoom in here. Let's get a little more specific. Canadian agriculture. This is a graph of Canadian agricultural emissions over the 28-year period, 1990 to 2018. And lots of different kinds of emissions there. The green ones on the bottom are mostly nitrogen fertilizers. So the dark green is emissions from soils, nitrous oxide. Most of that comes from nitrogen fertilizer. The light green is carbon dioxide from the production of nitrogen fertilizer. That Koch brothers plant I just showed you, that's the kind of emissions that are coming out of there. Skip over those kind of brown and tan colored ones. The red in the middle, those are emissions from fuel. When people think about greenhouse gas emissions, they often think about carbon dioxide from exhaust pipes, tailpipes. For agriculture, that's not the case. It's not the major source. Fuel use is kind of a minor part. So that red in the middle is farm heating fuels, natural gas to heat barns and water and shops, gasoline for trucks, diesel for machinery, and some emissions from the production of electricity where fossil fuels are used to produce electricity, not in Manitoba though. And then on top, the blue, livestock emissions. So the dark blue is enteric methane out of the mouths of grazing livestock, so that's mostly cattle. And the light blue is manure from all livestock species, so hogs, chickens, and cattle as well. Not the stuff that's dropped in the fields, but the stuff that's managed and stored and applied. So that's what this graph shows us, but I really want to point out a couple of things. One, agricultural emissions are going up. They're up, I think, about 23% over the period of this graph. And the reason they're going up is nitrogen fertilizer. So the top line is trending upward because those nitrogen-related emissions are trending upward as well. That's what really drives it. It's not increasing emissions from fuel. Those emissions are actually going down slightly. It's not increasing emissions from livestock. Those are largely a function of herd size, and the Canadian herd is not getting bigger, it's getting smaller. So it's really nitrogen that is the driver when it comes to Canadian agricultural emissions. And the reality is, if agriculture is going to reduce its emissions, it's going to have to do something about nitrogen fertilizer. So again, this is the Canadian graph. So you can kind of see the bottom line here, the nitrogen related emissions are going up because nitrogen fertilizer tonnage is going up. So just to kind of summarize this part of the talk, and then I'm going to turn to income solutions and other solutions. We've made agriculture into a linear system, 9,900 years of circular flows, about 100 years of linear system. And what we're doing is we're pushing inputs into one end, and that's causing emissions to come out the other. Every atom of fossil fuel, of nitrogen, of phosphorus that we push into one end of our farming systems comes out the other end. Some of that is benign, but some of it is quite damaging. And the key to understand is this: if you want to think your way through how you reduce emissions, the most important thing you can know is this, and that is the quantity of greenhouse gases coming out of agriculture is a direct function of the quantity of inputs going in. You push in millions of tons of nitrogen, out the other end come millions of tons of nitrous oxide greenhouse gas. You push in hundreds of thousands of tons of fossil fuel, out the other end comes a whole bunch of carbon dioxide. So another way of thinking about this is equally enlightening, and it goes like this. Agriculture doesn't produce greenhouse gas emissions. Agricultural inputs produce greenhouse gas emissions. And we know that absolutely 100% for sure without any possibility of contradiction because we have 10,000 years of data. And for 9,900 years, farmers farmed and they didn't use inputs and they didn't affect the atmosphere or the climate. 9,900 years of farming and not any effect whatsoever on the atmosphere or the climate because there was no inputs going in one end, there was no emissions coming out the other. And what this tells us is something really important and foundational moving forward, and that is any low emission food system will be a low input food system. Low input agriculture is the future, not zero input, not no nitrogen, not no chemicals. It doesn't have to be organic, but it has to be a type of agriculture that deals very respectfully and efficiently with these precious and if overused, damaging inputs. We just have to be more careful and efficient and mindful in the way we use them. We don't have to eliminate it, but we can't keep doing what we're doing, which is doubling and redoubling the use of fertilizers, chemicals, etc. So again, farming doesn't produce emissions, inputs produce emissions. We know that because of our 10,000 years of data. So we've got to move toward low input food systems so they can have low input food systems. Sorry, we have to move toward low input systems so we can have low emission systems. And people get worried when we talk about this, but really this can be part of a solution and it can be part of a net income solution. Michael mentioned before the talk about the net income graph that I've shared, and I'm going to share it again now and just show that the steps that we take to solve the emissions problem can also help us solve the net income problem that many farmers have. So this is a graph of Canadian gross farm revenue adjusted for inflation with subsidies subtracted out. That's the black line that goes up, covers about 90 plus years, starts in 1926, ends in about 2018. So what is that, 92 years? So the black line that goes up, it's adjusted for inflation. So what you're seeing there isn't just the effects of inflation, those are real changes over time. And we've subtracted out subsidy payments because those often mask what's happening in the market. So the black line is what farmers get from the market when they sell their grains and livestock, etc. The gray line is net farm income. That's again adjusted for inflation, and again subsidy payments are subtracted out so they don't mask what's really happening there. And I'll just make this a little easier to see. I'll color in the net farm income area green when it's positive and red when it's negative. You can see things haven't been very good in recent decades in Canada on the net income front. That's why we have record high debt, why every year taxpayers have to transfer between 2 and 4 billion a year to agriculture. But we could talk a lot about net farm income, but what I really wanted to focus on here was the gap between the top line and the bottom line. So I'll just color that in blue. That blue area is the difference between what farmers make and what they have left after they pay their bills. That blue area is equal to farmers' expenses. It's what they pay for inputs. It's the money they send to Nutrien and Exxon and Bayer, Monsanto and Deere, and to the bank in interest payments, and et cetera, et cetera. And you can see that blue area gets bigger and bigger and bigger. More and more of the money that farmers make from the market, and notice farmers are becoming more productive. The top line goes up and up and up. Farmers are doing what they're supposed to do. They're using the high-tech seeds, they're using fertilizer, they're using chemicals, they're using technology, and they're doubling and redoubling the amount of money that they generate from farming in Canada. We've doubled, tripled, quadrupled the output adjusted for inflation. So farmers are doing what they're supposed to do, increasing output. But notice what happens to that output is it's captured by others. The chunk taken by those input suppliers, that blue area, just gets bigger and bigger. So I'll just put some numbers here to that. From the end of the Great Depression till the mid-'80s, on average, farmers kept about a third of the money they generated from the market. But in the most recent generation or two, the mid-'80s until now, farmers are keeping about 5 cents. And the input suppliers are taking, extracting, capturing 95 cents on every dollar that farmers make. I would argue that farmers have made themselves over-dependent on purchased inputs. Imagine if farmers were keeping a third instead of 1/20th. Some of the effects of, if you've got a graph that looks like this, where someone else is taking 95% of your money, you get things like this, where debt goes up and up and up. Over the last 25 or 30 years, every year it goes up. It's now over 115 billion, which is more than some countries. You get graphs like this. This is the number of young farmers in Canada, farmers under the age of 35. 2/3 have been pushed off the land. We had almost 80,000 in 1991. We now have about 25,000. If we can't reverse this, if we can't get young people back to our farms, Canadian agriculture is going to plunge off a demographic cliff. If there's no young farmers out in the rural areas to take over those farms, a lot of those farms are just going to have to terminate, and we're going to go from having not that many farms now to having very, very few in the future. So I don't think farmers should be concerned. I don't think farmers should be overly concerned by this idea that we have to move to lower input agriculture, because high energy, high input, high emission agriculture has been bad for farmers. We've had an on again, off again income crisis for 35 years. Nearly a third of all farmers in Canada have been pushed off since the 90s, 2/3 of young farmers. Debt's at a record high. And the only way that the wheels have been kept on for a lot of the last 35 years is chronic transfers from non-farmers into farming. It now totals about 100 billion. Off-farm income, on it goes. It just hasn't been that good. So, solutions. The farm income problem and the emissions problem have the same cause, and that is an over-dependence on purchased inputs. What we say in the tackling report is that when farmers are sort of pushed to use too many inputs, their emissions go up and their margins and net incomes go down. So the solution to the emissions problem and the solution to the net income problem is the same. Reduce input overdependence. Find ways to use inputs more efficiently, more optimally, find alternatives to purchased inputs. A lot of the people on this call are doing exactly that. Names like regenerative agriculture, some might be pursuing organic agriculture, others are trying to find ways to use things like nitrogen more efficiently. So right now we have a high input, high emission, low margin farm model, and we need to transition to the opposite. I mean, more generally, outside of agriculture, we have an entire civilization that is replacing the circular flows of ecology with the linear flows of industry, and we need to do the opposite. And we have farm policies from Ottawa and the provincial capitals that drive farmers to get more of what they need from industry and less from biology, and we need to do the opposite. And as we make those changes to reduce emissions, we can also help restore farmers' margins and try and get some of those young people back onto our farms. So more specifically, we've talked a lot about nitrogen in the last couple slides I have. I think I'm coming up to time, Michael. I'm aware of that. In regard to nitrogen fertilizer, we need to use it more efficiently. So we need to use things like the 4R nitrogen efficiency, best management practices, right product, right place, right rate, right time. We need to use probably carbon capture and storage at production plants like the Koch plant I showed you, Koch brothers plant, maybe run some of those nitrogen plants with renewable energy if that's possible. Really important though, just going beyond technical tweaks around nitrogen, we need to find ways, we need to find alternatives to Haber-Bosch synthetic nitrogen. So one of the ways we do that is we protect and enrich our soils. We increase biodiversity through better rotations, including legumes. We use cover crops to capture some of that nitrogen, whether it comes from legumes or whether it comes from synthetic nitrogen. We use cover crops to capture it after the crop is done and hold it over winter and through spring. And in general, we diversify our approaches and pursue approaches that don't just maximize input use, approaches like regenerative agriculture, organic, and best possible grazing and agroecology. In general sense, what we need to do is we need to get more of what we need from biology and less from industry. That goes for nitrogen, but all the other inputs, etc. And at a policy level, sort of a Canada-wide level, we've got to change the prime directive of Canadian agriculture. We've got to abandon this maximum export, maximum production, maximum input, maximum emission model. And in general, we need to rediscover biology. A National Farmers Union member said to me, he says, you want a short history of agriculture? It's like this. When we discovered the plow, we enlisted physics into agriculture. With fertilizer and chemicals, we enlisted chemistry. Got the story wrong. Chemistry into agriculture. And now he says we need to rediscover biology. And I would add to that, we need to rediscover the circular flows that are the basis of the biosphere and agriculture for 9,900 years, and move away from these linear flow systems in which we punch more and more petro-industrial inputs into one end and get a bunch more emissions out the other. So I hope I haven't gone too far over time. Again, my name is Darren Qualman, and our material is at www.nfu.ca. And if you have questions or if you liked anything you heard today, I encourage you to read the Tackling the Farm Crisis and Climate Crisis report. So I'll stop sharing my screen. Hopefully there's some great comments and questions. Back to you, Michael.
Thanks, Darren. Yeah, that was great. Sort of a deep dive into understanding how we can possibly do agriculture better. I don't have a lot in the question so far. There's a single question here, Darren, about where does automation come in to this discussion?
I'll try and keep my answer short. If somebody wants more detail, I invite them to circle around again. We've got a crisis. Certain companies will try and use kind of a shock doctrine approach to turn that crisis into a sales opportunity. So we've got a lot of agricultural input corporations that will have us believe that the solution to the emissions problem is big data platforms and droids and bots and artificial intelligence and machine learning, and it's this long, long list, automation, etc. And that's how we get out of this. In a perfect world, that wouldn't be a bad idea. I really like technology myself. The problem is that it's a bit of a poison pill in that all of that data that's going to be moving around is going to be controlled by big companies like Bayer, Monsanto, or Deere. And because farmers aren't going to have control of that data, a lot of that data is going to be used to empower the other players in the system. So things like precision agriculture, variable rate, all of that, it would work a lot better if farmers had independent data platforms that could keep their data separate from the big companies that would otherwise make use of that.
Okay, thank you. Next question is from May. She writes here, linearity of N. How much nitrogen is exported as protein per acre, and how has that changed since 1930s? Maybe let's start with that. Let's go with, she's got a second question. So how much N is exported as protein per acre, and has that changed since the 30s?
Okay, so I can't give a quantitative number, but it's a constant. So a certain portion of every ton of wheat, a certain portion of every ton of canola, name your crop, you could actually look it up and you could figure out what percentage of each ton is N. And so the N export is a direct function of how many tons you're removing. So if a given farm finds a way to double its output since the 1930s, I think most farms in Manitoba would be producing 2 to 3 times the output they were in the 1930s for various reasons. So the N export per acre is probably between 2 and 3 times what it was. But what that is in kilograms, I can't tell you.
Right. And then after that, she has a comment, there are more people that need protein, and most of them are off the farm compared to most having lived on the farm in the 1930s.
Yeah, so it's partly a question about nutrient loops. When people lived on the farm, they ate and the nitrogen came out the other end and the phosphorus, and it didn't go far. What we've done, and I have a chapter in my book on this, if you think about nitrogen and protein, the nitrogen starts in a factory, it's trucked to your farm, it goes into your field, it goes into the crops. A significant portion of it stays in the crops. Those crops are trucked to the city. They're eaten by urban people. They end up in the toilet. They're flushed down. They go to the river. The river works like a great big conveyor belt, and it delivers that nitrogen out for deep ocean burial, where it's going to stay for hundreds of millions of years until the continents lift that back up into mountain ranges and it sort of weathers back onto the landscape. So yeah, there is a real problem with urbanization. Nobody wants to be without flush toilets, but when you have billions of people flushing, taking nitrogen from the landscape and flushing it down the toilet and down the river and into the ocean every day, you've got a significant linear problem in your civilization.
Right. I've been calling that, I think the fundamental problem, the 10,000-year-old problem in agriculture that we've still yet to come to terms with, is a broken mineral cycle where we are exporting off the land. And we've just accelerated that. Like what I've been saying in regards to Manitoba and phosphorus is, soon we're going to have to start mining the bottom of Lake Winnipeg, because that's where all our phosphorus will be, right?
Yeah, and some people that take an extreme position that want to do away with nitrogen fertilizer, for instance, the thing they have to grapple with is, if you've got this tremendous outflow on the sort of sewage and river end of your civilization, moving nitrogen out of the system, it's hard not to have an inflow at the other end in terms of synthetic nitrogen. Now, clearly we want to use less than we are now, but it's going to be hard to get to zero.
Good. Question from Ryan. When we export as much as we do, so he's talking about exporting our grains, our beef, or, we probably export what, 85% of what we grow in Canada, something like that, plus or minus. How do we create a circular economy if we're exporting?
Yeah, that's a good question, because it's a hard question. So on the farm, you make things as circular as you can by trying to find alternatives to linear flow fertilizer, trying to find ways to get nitrogen out of the air via legumes, for instance. Downstream in the city, I've toured our our sewage treatment plant here in Saskatoon, and they do something that's absolutely remarkable. They're one of the few sewage treatment plants in North America that does this. They're capturing phosphorus, but they're capturing it so well, they actually create perfect little white phosphorus fertilizer granules that you can take right out to the end of that sewage treatment plant and drop into your air drill. I didn't know they were doing that. They only do that in a few cities. Now, there's a critique of that one can make too, but wherever possible, we should be capturing all that nitrogen and phosphorus and not putting it in the rivers and sending it to the ocean.
Right. Diljit has a similar question. Does low input, low export also mean low production? And how does it impact our economy?
What we want to do, of course, is find ways to reduce inputs quite significantly, but reduce output very little, or maybe not at all. We certainly wouldn't want to embark on an agriculture in Canada that cut output by half. Some people might think we do, but I would argue it'd be very, very difficult to make that kind of work financially in Canada. So we might be willing to tolerate a small reduction in output, but still, production's up a whole lot, and a small reduction in output wouldn't be that significant. But the other thing we have to remember, what we do with all this output, we waste about 40% of the food we produce. We turn a lot of that output into biofuels, which in many cases are a little ill-conceived. People then pour those biofuels into really big cars and trucks. Got a bit of an echo there.
Yeah, I'm trying to mute them.
Yeah, so food waste, some ill-conceived biofuels. We turn a lot of that output, we feed it in feedlots where we turn 10 calories into 1 calorie, etc. So the system could certainly do with a little less volume if we used it better.
Good. Next question. Now, I think this is one of the big questions in ag. We really don't talk about it because I don't think we really know how to answer that. It's how do we do work without using fuel? Basically, we're a diesel fuel driven industry. How would we look to reduce our use of fossil fuels?
Yeah, that's a great question. And my answer is a bit speculative because the things I'm about to describe don't really exist right now. But it isn't in any way difficult to take off-the-shelf parts from Nissan or Chevrolet or Tesla and make yourself 100 horsepower. A company could make itself a 100 horsepower tractor. So all the shore tractors and small and medium-sized tractors could be battery electric. They would run for 4 to 6 hours between charges, and if you got ambitious, you could do much better than that. So for smaller equipment and half-ton trucks, for instance, all of that can be electrified with batteries. The larger equipment, big combines, big tractors, big sprayers, hard to say. Maybe hydrogen compressed, maybe hydrogen using anhydrous ammonia as a carrier. But all of that's going to be worked out in the trucking sector. We as farmers, we don't really have to figure that one out. The long haul trucking sector is going to figure out whether those trucks are going to be battery electric or whether those trucks are going to be hydrogen, etc. And I think they are going to work that out. I think 10 years from now, a lot of the road tractors, road trucks are going to be non-fossil fuel. And those engines, it's not difficult. In many cases, the engines in those trucks and the engines in your tractors and combines are the same engines from Perkins. Cummins is a big hydrogen company now. So I think that's what's going to happen. They'll work it out in long haul trucking, and then they'll transplant those drivetrains into agricultural equipment.
Right. I think you could make an argument that do we need those large equipment? If we have more people on the land, farms start to perhaps go down in size. We're oriented to continue to get bigger and bigger, but if we could change that, then why do we need a 600 horsepower tractor? Maybe and if we do things like maybe think about reducing tillage where we're not dragging, that's where you take huge horsepower to drag steel through soil, then we can probably get away with, like, I think I saw there the other day, John Deere has a 400 horsepower electric tractor in the works. That's pretty much ready to go.
And there was a question before about automation, and
Yep.
some people think that you just have 10, 50 horsepower tractors, but I'd have to see the economics of that one. But yeah, there's a number of things on the horizon, perhaps.
Yeah. What do you think of all the large companies that are going to be carbon neutral by 2050?
I have a lot of misgivings around carbon neutral talk. And boy, we could have a whole talk about that. But here's the crux of it. When you take carbon from fossil fuels, those fossil fuels have been in the ground for hundreds of millions of years. Like, they are really hyper stable. If you didn't go to all the trouble of digging them up, that carbon would stay in the ground. It would not get into the atmosphere. So as soon as you dig it up and burn it, you've put it in the atmosphere. It's going to stay in the atmosphere for 1,000 years. So 1,000 years is kind of the lifetime of carbon in the atmosphere. A lot of the carbon neutral and net zero stuff is taking that fossil fuel carbon, and putting it in soils and trees, but it doesn't stay in soils and trees for 1,000 years. So I just think there's an imbalance in longevity, whereas that carbon atom in the atmosphere could be there for 1,000 years. I don't think that you can permanently move it into trees and soil.
That's interesting. There's more of a flow than a sequestration.
Yeah, see, soils and air and plants are kind of an active biological pool that constantly exchange, and fossil fuels in the ground are completely cut off from that. But once you take carbon from fossil fuels in the ground and put it into that active biological system of plants, soil, and air, the plant, soil, and air try and exchange carbon. I mean, that's what biospheric systems do. So it's difficult to sort of put it in the soil and then have it stay in the soil. But I don't want to take away from the fact, I mean, I know soil carbon building is real. I know people do that, and it's tremendously important. So I'm not in any way impugning that or questioning that the fact that through good grazing and good cropping practices, people can dramatically increase carbon levels.
Right.
Just had to say that before somebody took a tomahawk or took a stick.
No, yeah, absolutely correct. Yeah, it makes me think, like you were talking about life there, like, we have to realize that life is a carbon-based system, right? And with that carbon available, life will do things with it, right?
Yep.
David, you want to comment?
Yeah, I asked that last question, but I guess to me, they're going to be buying credits, but they're actually not going to be reducing their fossil fuel use. So that's the biggest problem. Because I saw it the other day that there's a Russian tanker bringing compressed natural gas to Europe to distribute through Shell, and they called it carbon neutral.
Oh.
Can't be, but that's what they're doing.
Michael, there's a lot of really smart people on this call here. So, I mean, this doesn't have to be a bunch of questions to me. Other people probably have some things they just want to say. So I
Sure.
invite them to do that, and I can listen for a while.
Okay. I think that one of the comments we had from a producer the other day was on this issue of carbon offsets, and really feeling strongly that, there's almost like an ethical issue here, that he didn't want to be involved in a carbon offset as a farmer, right? That wasn't really, that's just a shell game and not really fundamentally accomplishing anything as far as, reducing, say, atmospheric CO2 levels, right?
Yeah, that's a great argument. And I have to say, I've spent much of the last 3 or 4 days grinding through the new regulations on offsets, and it's a maze, and who knows what will come out of that. There's a lot of talk about permanence and additionality, and even if you take our best case scenario, I'm not sure that things like zero till and a lot of what farmers want to get paid for could fit into what the federal government's planning right now, just because of difficulty meeting the additionality and permanence requirements. But it's very hard to say. It's quite murky.
Right. Well, we could open it up if someone wanted to unmute and ask a question, or I can continue. We still have a list of questions here, so I can pause for a moment if someone would like to post a question or a comment. Okay.
I've got
Ryan?
a
Okay.
question or comment here.
Yep.
So is there a scenario that with these massively increased carbon dioxide levels that plant production just ramps up and we come to a new equilibrium? Sure, the sea level is going to rise. Obviously, there'd be a lot of hurt on the peripherals where everybody lives on the shorelines. But like in a greenhouse scenario, I don't know the exact parts per millions, but productivity will go up in the biological world where it's not underwater. Is there a scenario that the world won't end in catastrophe under high levels of CO2?
No. Sorry. Thanks for the question, Ryan. So, yeah, just a great question. So, and you probably know some of this. If you held the other things constant, if you just increase CO2 and it didn't get hotter, because heat can cause stress to plants, and if the water continued to fall in the way that you want it to fall, plants would be more productive, absolutely, because they wouldn't have to open their pores as much to get the CO2 they wanted, so they wouldn't lose as much water, and they just become more productive. Unfortunately, it's going to be a hotter world, so the rise in temperature will offset most or all or more than the CO2 fertilization effect. The other problem, though, too, is even if the plant mass that we have got more productive, it would still be a fraction of the productivity we used to have. Because you have to remember, the earth used to be full of grassland that was green, 150 plus days of the year. And now it's crops that are green and growing for only a fraction of that. And it used to be full of forests that were huge, layered forests. Now it's just grassland or cropland. So I think Michael was reiterating this to me the other day, that we've probably taken about half of the plant biomass off the earth in cutting the forests and replacing perennial crops with annuals, etc. So even if what's growing now became more productive, it still in no way would be as productive as the biosphere was a couple hundred years ago.
And of course, one of the consequences of that is we've cut the actual CO2 capture globally per year in half, like roughly, I think the numbers are 10,000 years ago, like pre-agriculture, we sequestered about 250 billion tons of carbon per year. And now the estimated planetary carbon sequestration is about half that, about 130 billion tons. So and if you think about that in terms of energy, it's like having half a battery, because really what that means is you're converting solar energy into chemical energy, right? Photosynthesis, CO2 and water, green leaf. And that's sort of like having half of a battery in your cell phone now. So that has consequences for things like soil and so on. And it's just our ability to possibly pull a little more carbon out of the atmosphere. But Ryan, I kind of read, and I can't remember the exact details, but that was sort of the question, right? Because in the greenhouse industry, they pump up CO2 levels and it increases production. But there's other things that limit like maximum production. And I think for us on the prairies, the number one factor, if I remember correctly, is day length.
Not water?
No, it's well, yeah, water, but I think it's actually day length that the plant sort of, it goes through that cycle and it says, hey, I'm done, right? Regardless of what CO2 levels or whatever, right? It knows that it's the end of the growing season. So if I remember correctly, it would be day length. But yeah, water, I'm thinking more like physiological limitations rather than say like, environmental limitations like water or temperature. Right? And the other comment, and Darren mentioned it, was, it's the speed of change, right? It's not just the scale, but it's the insane speed, and the speed of change is probably potentially more of an issue than the scale. So the speed at which the rate of change is, as far as we know, it's unprecedented in history of the planet. That'd be correct, Darren?
Certainly the speed of just about all the change. You can find lots of books with titles like The Great Acceleration. Just while we're waiting for the next comment or question, I just want to flag one thing that's happening. People really like the Tackling the Farm Crisis and the Climate Crisis report. And tomorrow morning, we're coming out with a new report on emissions reduction and climate solutions called Imagine If, Envisioning a Near Zero Emission Farm and Food System for Canada. And what this report that we release tomorrow is going to do is it's going to take the viewpoint that we're in 2030 and we're looking back over the 2020s and all the things that we did positive in order to get on top of the emissions problem from the farm and food systems. But more than that, all the other benefits that we created as we took steps to reduce input use and increase margins and get young people back to the farms. It is a truly positive and hopeful look at what we might do over the next 10 years.
I like the title. I think one of the issues we've had in agriculture and say, the green revolution years is a lack of imagination and creativity. And I think there's a lot of things especially around nitrogen, we can really make some, and we maybe won't get into those details here tonight, but it's part of the work that a number of people are doing that are on this call. And there's lots of positive, creative solutions that are kind of in the works. Anybody want to make a comment? Brian?
Michael, I've got a question. I typed it earlier, but Darren, I really enjoyed the talk so far. Brings me to a question. I was listening to John Kemp just this week on a podcast. He wanted to tax farmers for the overuse of nitrogen. He wasn't talking about taxing completely for any use, but he was talking to a Neufeld scholar out of Great Britain about this. And it really kind of hit home today when my second career is I work as a crop adjuster for crop insurance. And I was at a producer today and he told me he used 145 pounds of nitrogen for his wheat crop. Kind of blew me away because his wheat only went 50 bushels the acre. And now he doesn't know if he's going to go that high. What do you think about the taxing of overuse? And I think 145 pounds of nitrogen is a little too high. And the second part is John Kemp also believes that the application of nitrogen in the fall, there could be losses of up to 35%. He said the only one that is benefiting is the retailer because it's their slow period. So what do you think of those?
Yeah, thanks, Brian, for that. You referenced John Kemp a couple of times. I didn't know his work. Many of you probably do know his work. I didn't know it until I spent a day virtually at a US ag forum. And John, I think, had about 3 hours on there. And I was just amazed, you know, just when you think you know half of what you need to know, you encounter somebody like that and realize you only know a tenth of what you need to know. He's
That was
quite
that-
an astonishing human being.
That was that Bismarck
Yeah,
conference
no-till.
a couple days ago.
No, this was one month ago. No-till on the plains out of Wichita, Kansas.
Yes, right.
Yeah. So in terms of a tax, I don't think that taxing farmers is a good idea, especially if you don't give them a way to get the money back. Like, we've floated some ideas about how you might put a carbon tax on agriculture, but the key thing is it's a carbon tax and refund system where all the money that goes into the taxation comes out to those people that find ways to solve those problems. So, but having said that, we do need to find ways to curb excess end use. The thing that we're promoting to government right now isn't a stick like a tax. What we're promoting to government is the idea that farmers need incredible support to find alternatives to nitrogen, to implement efficiency programs. And we met with the Minister of Agriculture federally here last month and said, we need 1,000 independent public servant agrologists. And those agrologists need to go out there and they need to promote low input use, input reduction, alternatives to purchased inputs, low emission, all the things that the industry linked agrologists maybe aren't or can't focus on. And we need really good independent soil testing. And the way you can get farmers to pay attention and make the moves is to give them for free this agrological support that otherwise they'd have to pay for. Farmers who are willing to play ball and look for ways to use less and emit less greenhouse gases, their reward is they get free agronomic support, free soil testing, and sort of independent, non-biased stuff. And yeah, just briefly on your next question, I completely agree. Fall applied nitrogen isn't as good as spring applied, and that's what the 4R people tell us too.
Well,
Can I jump in? Daljit here.
Go ahead.
Thank you. Darren, to your point about public extension system and public agrologists, I strongly trust in this system, but we are not on that path if we talk about the provincial politics. Recently, we closed more than 21 ag offices. And how do you think that we would be able to achieve what we are thinking we should achieve?
Yeah, thanks, Diljit. Absolutely. Whether we look at Saskatchewan or Alberta, recently closed a bunch of their ag research and extension, Manitoba too. You're right, we're moving in the wrong direction. We're turning most of this education and extension and outreach work over to the private sector, either sort of agrologists linked to the companies that are trying to sell inputs or private companies out there. And, I know a lot of those people are doing fantastic work, so I don't want to take too much away from them, but it doesn't appear that we've got the people out there that are really pushing low input, low emission systems. So what we're saying is we need those public servant agrologists. We need to start about 1,000 of them. And going a little further, we said to the minister, you need to create or recreate something like the PFRA. So instead of the Prairie Farm Rehabilitation Administration, we're saying we need a new CFRA, a Canadian Farm Resilience Agency. And that CFRA can hire and manage those 1,000 or 2,000 agrologists. They can run demonstration farms. They can administer the free soil testing. They can work with farmers to preserve or restore wetlands. There's just a whole bunch of things that we need to do around climate and emissions that just aren't going to get done unless the government really weighs in with some muscle here.
Can I make a quick comment on that, Darren?
Sure.
I strongly disagree that it's an information issue that's why farmers are not soil testing or using an input intensive system. Like, I think it's a policy issue. There's too many supports, the crop insurance, the income stability, and it's just simple economics. Like Brian says, a farmer put 140 pounds of nitrogen on. Well, I know that's a common thing, and these guys are pushing yields. And so when that guy put that 150 pounds of nitrogen on, it was 30 cents a pound, or 40 cents a pound nitrogen. It just made sense to put it on. And I think in the information age of the internet and sharing of knowledge on social media, I can't see how the government would do a better job than farmer networks would do or are doing now. If there was a better economic incentive, it would be happening already, I think, a lower input system. And I just, and from personal experience, when we don't put on the fertilizer, we don't get the yield, and the economic return isn't there. Not saying that we could do things differently or a more holistic type management to improve that, but I'd say if anything, the government needs to do their hand in more research to get those systems, like what John Kemp talks about, dialed in more locally. But soil testing and telling farmers to use less fertilizer, I think that's dead in the water. That's just my opinion. So,
No, I appreciate those comments. I'll take that to heart. Thank you.
Well, don't take it to heart, but
But yeah, I think maybe it's in the details here. Is one thing we're talking about soil testing. Exactly what are we talking about? Like there's different types of soil tests, and we have to be kind of honest. All soil tests are flawed in one way or another. Some may be useful. Like it appears in, my opinion, that like a standard soil test, conventional soil test, where like, for example, talking about nitrogen, where you're really just looking at nitrate, and is almost, useless, except if you're applying fertilizer. It doesn't give you any sort of meaningful measure of what's really going on with nitrogen. So I think soil testing can be useful, and one of the soil tests that we're using is the Haney Test, which gives you a deeper look at nitrogen, where you're not just looking at nitrate N, you're looking at many forms of N that are potentially tied up with carbon, where conventional tests can't really get a look at that. And so when you look at the difference, it's sometimes quite shocking. In a lot of cases, especially in like high input conventional grain farms on the prairies, there can be a difference of up to like 100 pounds of N per acre between what the conventional soil test is seeing in nitrate and what's really available to the plant. That is huge, which makes now you get a sense of how much they're over applying nitrogen. And so we asked the lab that we work with, they've conducted tens of thousands of Haney tests now over many years. Just asked them the question, in their opinion, based on the tests that they've conducted, what percentage of farmers, so now this is Canada and the US. So it may be skewed a little bit towards the US, corn, soybean country. But in his estimate, 85% of farmers are over applying nitrogen.
But that's the point exactly, Michael. Why are we applying nitrogen? We just saw the graph showing that nitrogen it's a disaster, the amount of nitrogen that we're injecting into these systems.
No, it's exactly as you say.
We're biological nitrogen fixation to easily supply all of our needs.
Right. We're oriented to make those decisions by economics. You're absolutely correct. Yeah. So like many, difficult problems, it's complex, and it's probably never going to be just a single variable in a complex system. Right.
Yep.
But yeah, good comments. Thanks, Ryan. But I think I think still education is going to be a big part of it. It's easy enough to Google something, that's fine, but there's still probably going to be a need for some form of sort of deeper understanding of these issues that that. But these like farmer networks or that sort of thing, and can be super useful, and I think will drive the change.
Yeah, the circular knowledge,
Yeah.
I really like that, Darren. I think, and I guess maybe that's what you're getting at with the government agencies supporting that, because that's exactly where we need to be. We got to be out in the field observing more, figuring out what works in our own environment and context.
Yeah, I think that word observation is going to be critical. We need to become more observant. We've sort of lost that skill in agriculture, and we need to do a better job of observing what's going on in our local situation and use that knowledge. Like Darren talked about seeds, for example. Seeds are interesting in that, we buy some new genetics, supposedly that'll be the thing. And I'm not saying genetics hasn't been a big deal. Of course it has. But in a lot of cases, those seeds are not grown locally. They're not adapted to those set of conditions that your farm has. Now contrast that to someone who's been growing their own seeds and reusing them, which is the way we did agriculture for thousands of years. And not just plants, not just seeds, but animals as well become adapted to their environment. And in a lot of cases, we've lost that local adaptation, and that has consequences too. Questions, comments?
Darren, sorry again. Darren, I like your idea about bringing more people on the farm, especially young people, and maybe a kind of working against consolidation of land at a faster pace. Any pointers? How part of that?
Yeah, thank you, Diljit. I mean, there's a number of problems here. One is just consolidation of land. Apart from a lot of the things we talked about here tonight, we've got another problem in especially prairie agriculture, and that is kind of this positive feedback and ratchet effect, wherein when land comes up for sale, the people best positioned and most able to buy it are the biggest farmers. And this is not slowing. In many ways, it's accelerating. And we're going to get to a point here in the future where there just aren't going to be a lot of people needed to farm. And those farms are going to be very, very large units. And I think as a public policy point in Canada, we need to decide whether we're okay with a future where there are only a few thousand farm families sort of farming Manitoba, or whether we want to intervene and maintain larger numbers of ownership units in a province like Manitoba or Saskatchewan. I think it's an open question right now, but the trend lines are very, very clear, and we're going to lose, half of our farmers in the next generation or two if we don't intervene in these markets.
Can I ask a question, Michael?
Yep. Go ahead.
It's actually from my dad, but
Okay.
what is it?
Well, Michael,
yeah.
I was just
Hey,
wondering, hi, Michael.
Hey.
How is it that such a societal, and I mean it's a global societal problem, boils down to getting farmers to change?
Do you want to expand on that a little bit?
Well, this is a huge problem you're talking about, and just farmers are never going to change it by themselves.
Yeah.
And so we're like preaching to the choir right here amongst ourselves. That's not going to fix it.
Yeah, that's a really great point, and one I should have underscored a little more. This transition from circular to linear systems isn't an agricultural problem.
Yeah.
It is the thing that we've done in every single system in our civilization.
It's clothes. It's, because we used to have, it was a cottage industry to make cloth.
Mm-hmm. Yeah, so the thing that has made us as rich and powerful and prosperous and sort of rich in consumer goods, it's this these linear flow systems.
Sure, absolutely.
But these linear flow systems are also causing massive problems, and I outlined some of them, everything from climate change to oceans full of plastics to resource depletion, and on it goes. So we as a civilization, not just we as farmers, we as a civilization have to find ways to move back toward something that looks more like a biosphere. And a biosphere, you know, somebody once asked me what sustainability is. And I said, I know exactly what sustainability is. I know what it is because it's what the biosphere has done for hundreds of millions of years. And that is move materials in circles and power the whole thing by the sun. Circular flows of material and solar energy, that is sustainability. And that's exactly the opposite of what we've done in our civilization. And that's what we need. You know, we can't fully re-embrace that, but that's the direction we need to go.
Yeah, that sounds so great. But I don't know. It's pretty discouraging. That's all I wanted to say, Michael.
Thanks, Tom. Anybody else?
Just one
Brian?
other note. I think I've been farming a little too long in the regenerative mode now, and I've become very cynical about whatever my input companies have to say because I don't believe them at all. And I've also had a son work in the industry for a year that he saw that it was push as much as you can onto the farmer, and he didn't like it either. So he's now working out west. But I think, unfortunately, we have too many farmers with too much on their plate. They're running big operations, and they're going with the direction that their input companies are telling them what to do because they don't have the time to look it up themselves. And unfortunately, I think we're going to see more product going through these farms. And it costs a lot to put in a crop, but this is how we've been doing it for years, and they can't see outside of the box.
Yeah, good comments.
Darren, what would an intervention look like? Like you said, we could make a decision to embrace smaller farmers or try to divert the consolidation. What would that look like?
I don't completely know, Ryan. I mean, I think we could all brainstorm a number of things. Prince Edward Island has caps on ownership. We might try some parallel systems. Like right now, we allocate farmland according to ability to pay. And continuing to allocate farmland only by ability to pay means those with the greatest ability to pay will end up owning all the farmland. And it's both a positive feedback and a ratchet effect because it's very hard to imagine how that ever reverses short of calamity. So we might start taking some of that farmland and allocating it in different ways to young farmers, etc. I'll give you something I've been thinking of lately. The federal deficit this year is $381 billion. And the deficit next year is going to be probably the better part of 200 billion or more. It adds up to about $650 billion. By coincidence, $650 billion is the value of all the farmland, buildings, capital, machinery, inventory, everything on every farm in Canada. So the amount of money that the government has borrowed in the last 2 years, they could write a check they could write a check for all the farmland and buildings, etc. in Canada. So what that says is there's capacity there to maybe purchase some of that land and start allocating it on the basis other than the ability to pay. But I mean, that's not policy in any way. I'm just blue skying some ideas, but both limits and maybe some government allocation by other methods might be tried.
20 years ago at university, I sat in on a lecture by Vaclav Smil, and he made a comment just like off the cuff, and he said the government of Canada would be way better off just to write every farmer in Canada a check for $1 million and walk away from from supporting the egg industry. So that's funny. We'd have been better off doing that 20 years ago, I guess. Cheaper anyway.
Yeah, Smil says some provocative things.
Yeah.
Yeah. Last couple questions here. Maybe we'll do that and then we can see where we're at. Please comment on how the rest of the world will feed itself, or at least the ones that currently buy our food.
Again, you could have a whole evening on the question of feeding the world. I'll tell you a way I heard that question answered that stuck with me, and you can argue against it. There's a lot of different ways to approach this, but somebody asked a farm leader about feeding the world, and this farm leader said, well, I've been to many places in the world, and like us, people don't want to be fed. They want to feed themselves. So pick your country. They don't really want to be dependent on Canadian grains and food. They want to be dependent on food from their own country. Unfortunately, the huge quantities of very low-priced food that comes sloshing out of places like North America comes into these markets and damages their local farmers and makes it more difficult for them to feed themselves. So, you know, I think Canada will always be an exporter, but I think we just need to be a little more humble about what feeding the world means, because to some extent it can create positives, but to some extent that low price grain crashing into those local markets can also be very damaging to the producers that are in those places trying to produce food for the people around them as well.
I hadn't heard it described that way. That's interesting. And I think our final question here is about nitrogen in the fall. So nitrogen fall applied. Isn't it like having supper at 9 p.m. every day, and then that is all you get to eat until 9 p.m. the next day when you are running a race at 10 a.m. the next morning? Rough.
Yeah, there's that, and some of you'll know nitrous oxide emissions from nitrogen. It's largely a function of the water content in the soil. So it's partially saturated soils that cause a partial anaerobic phase in the soil. And that's when you get these real big plumes of nitrous oxide from nitrogen fertilizer. So you don't want to have nitrogen in the ground when the ground is soaked. So that spring thaw is a real point where you get a lot of nitrous oxide. And also you want to have as little nitrogen in the ground as you can. So the best way to reduce those emissions would be to apply it about the time the plant can use it in the spring, and even better if you applied half of it when the seed went in, and if you found another way to put more of it in when the plant's growing, although I know that that's functionally difficult for a lot of the crops we grow here. It's easier if you're growing corn, for instance, but not easy if you've got 10,000 acres of cereals and out there. So yeah, putting it in the spring is better than the fall for emissions reasons and probably agronomic as well.
Right.
Can I ask one more question,
Sure.
Michael?
Go ahead, Ted.
You talked about maybe the moving into a biological solutions to the problem. Have you read that any from Yuval Harari? Like Homo sapiens and Homo Deus?
I read the first one, I read Sapiens.
Okay, so like he talks a lot about this synthetic biology that could come along or that could change humans and everything else. Like, I mean, based on how humans use technology to, you know, basically carbon usage for fertility and everything else in the modern age, it would make sense that they would apply biology in the same way to solve maybe some of these problems that we've created through the excess carbon phase of society. I just want to hear your thoughts, maybe.
Maybe just say a little bit more about that, because I don't want to answer the wrong question here.
Well, I mean, it's like it seems to me like we know that we have all these algae plumes from all this phosphorus, so rather than correcting the problem, we'll just create something to dump into all these water bodies that will use up the phosphorus in some way that we can better extract it. You know what I mean? So it's kind of using a biological model to fix our own human problems, which will probably create other problems, but we don't know them yet.
Yeah, you raise a lot of good points. I'll just focus on one. You've often heard the phrase "end of pipe solutions," and that's exactly what we can't do. I don't think there are good end of pipe solutions. We create these linear systems, and if you insist on punching 100 million tons of N in one end and it comes out the other, I don't think there's anything you can do at the end of that pipe to fix that outflow of 100 million tons of N per year. You've got to restrict the amount going into the intake end. I think you can do some things around the end that are okay in terms of lakes and rivers and oceans, but really that's only a stopgap. You've got to stop pushing so much in, and you've got to stop increasing every year the amount you push in. Harari's quite a techno-optimist. His faith in technology exceeds mine by quite a bit.
You're more a European pessimist like Vaclav Spiel.
Yeah.
All right. Well, that's this has been excellent, and maybe that's a good place to wrap things up. So thank you very much, Darren.
Well, thanks to everyone that's spent part of their evening here tonight. Really appreciate the opportunity to share ideas with everybody.
Yeah. And just so everyone knows, that we do have a Manitoba Grazing Club YouTube channel, and I'll be posting this there for you to rewatch. Also mention that we have a number of other interesting videos, so check them out and let me know your feedback. Thank you very much, Darren. Have a good evening, and we'll talk again maybe on some of these topics again.
Great. Thanks, everyone.
Thank you. Good night.
Night.